creek slow, bare feet brushing the grass below, moonlight spilling on your golden hair. I take a deep breath, you're unaware. My hands are nervous, I grip the chain, words in my chest like falling rain. I steal a glance, your cowboy grin, wondering if I should let you in. Swinging hearts beneath the stars, I confess I've loved you from afar. You look at me, your eyes so true and say, I've been waiting for you. The night sits heavy, the crickets sing, the air is thick with everything. I fumble through words raw and shy, but you just smile and catch my eye. Then you pull me closer, fingers tight on mine. You laugh and whisper, took you some time, with the world on pause and a breath so still. You kiss me soft like I dreamed you will. Swinging hearts beneath the stars, I confess I've loved you from afar. You look at me, your eyes so true and say, I've been waiting for you. Swinging hearts beneath the stars, I confess I've loved you from afar. You look at me, your eyes so true and say, I've been waiting for you. Under the oak tree, the swing creek.
Alrighty, y'all, welcome back to day two of AP Physics C Mechanics live stream. We're live again, once again. Welcome everyone, welcome.
Thank you.
Welcome.
So, we're gonna go ahead and get started with a resumption of the problem that was posited yesterday before I had to go, which was our practice problem here. So let's go ahead and start. So, what work is done by what force in this example where the particular ball accumulates kinetic energy when it's dropped 50 centimeters? What work is done by what force, Robin?
It's gravity that's doing the work.
Okay, it's gravity, and what?
The FG.
And how much work is being done?
1.25.
Correct.
And if it's, yeah, I was gonna say it didn't specify it was an open and closed system, so I counted if it wasn't or wasn't. But yeah.
Well, I mean, particular ball. We're talking about a ball right here, so we're not talking about the ball.
Okay, yeah.
Okay. So
Okay.
now we're gonna lower the ball, the same ball, rest to rest. Jacob, how much work is done by the force of gravity?
0.
Incorrect. Gravity's still doing work. Just because it's going from rest to rest and you're bringing it down doesn't mean that gravity is not doing work. So work is 1.25 joules. What is the net work, however?
The network.
What is the network? Robin?
Network is your net worth.
Robin, what is the network?
Okay, the network I got was, correct me if I'm wrong, but is it 2.5?
Nope, incorrect.
No, sorry.
It's
Yeah.
0 because the
Oh,
network is,
yeah,
is
yeah,
the
I remember,
changing
wait,
kinetic energy, which
No,
is
yeah.
1/2 mv final squared minus 1/2 mv initial squared. V final is what? It's at rest, 0.
Yeah.
V initial is at what? It's at rest, so it's
Rest,
0.
0.
So it's equal to 0. So what is the work done by the force of the person? Jacob.
Jacob, come on.
What's the work done by the force of the person? 0?
No. We know that the network is 0. We know that the work done by gravity is 1.25. Well, better said, the network is equal to the work by the force of gravity plus the work by the force of the person, right?
So
The
it has to be
network
negative
we know is
1.5.
0. The work
So-
done by the force of gravity is 1.25. So the work done by the person
It's
is
negative 1.25.
negative 1.25 joules.
Negative.
Got it?
Yeah.
Question.
Also, but oh, wait.
So
before
not
I-
only does network equal delta K, it's also equal to work by force 1 plus work by force 2. Alrighty? Any preguntas?
I know something I want to quickly say is that so pretty much that's just me. What's whatever. No, let's continue.
Alright, let's continue then. Let's go ahead. So now we're going to go more into detail about conservative and non-conservative forces and just kind of explain to you guys some things about them. So conservative forces store energy in associated, so conservative force, I'm just going to denote it like that, store energy in associated, I misspelled that. Yeah, associated U's. Alright? So an associated potential energies. What that means is that they do 0 work on a closed path. So do 0 work on a closed path. And let's analyze it. When we have a ball that goes up and then back down, this is our path, right? The force of gravity here, on this one right here, when the ball's going up, what direction is the force of gravity?
Force of gravity is always down.
Negative, right? So force of
Yeah.
gravity is like this. So is our work going to be positive or negative? Our work by gravity.
Work by gravity has to be negative.
Yes. And then on the right, what direction is the force of gravity?
On the right, it's up.
It's down. The force of gravity is always
I mean,
down.
sorry.
So is
Never
this
mind.
giving energy or taking away energy from the system?
It's giving energy.
This is giving energy to the system. So the work done by
Yeah.
gravity is what?
Positive.
It's positive, correct. Alright.
Okay, so pretty much if an object goes counter to gravity's direction, which is always down, it will make work by gravity will be negative. But
Yes,
if
exactly. Because
the object is going the same direction as gravity,
you're adding kinetic energy and the earth is taking it away. When you throw something up, it has kinetic energy and the earth is taking away that kinetic energy.
yeah, it's causing
And when it
resistance.
comes back down to that same level, the net work due to gravity is 0. Because it's going up then back down. It's taking away energy and then it's giving it right back. Alright?
Yeah.
So the work is also path independent. So this does path independent work. What that means is if we have a ball that goes from here to here, what direction is gravity?
Always down.
Down.
So that means work by gravity is negative.
So work by exactly, good job. Work by gravity is negative. But now let's say, right, we have something that goes up and then down again, what's going to happen? Well, gravity we know is down. So
up and then down. So at first, work by gravity is going to be negative, but once it reaches like the point where it starts to fall again, where it'll work by gravity will become positive.
Sorry, what happened? What were you saying?
I said pretty much until it reaches the point where the ball starts to fall, work by gravity will be negative until the work by gravity starts to decrease.
Until gravity starts giving it energy.
Yeah, when it reaches the point of its
this is in a ball system. We're not looking, because remember the work here would be zero because you're the work is equal to the mechanical energy, or better said, the work would not be zero, but the net work would be zero because you have like the force of gravity is an internal force, is better said. Yeah, like look, for example, here we're talking about here work is zero because you're accounting for the Earth in the system. So our changing kinetic energy gets immediately converted into potential energy. But here we're just looking at the ball. So the work done by gravity is zero. This could even involve the system because it's work being done by a force. It's just whether the force is internal or external that matters, and what our system is. But I digress. So here, all of this right here, work is negative. But here, work is positive. The work done by gravity is positive. So the only difference here, this would be WG net, because then this is the negative and then this is the positive. So this is your net work. Got it? Think about this as like extra positive, and then this is just extra negative. Okay? From here to here is just extra negative. All right, any questions on conservative forces?
No, you explained it really well.
Any questions, Jacob?
Actually, a quick question, if you don't mind. This is just an idea I have. What happens if, per se, let's say, like, a ball falls. In its starts trajectory, it falls, and then it collides with the ground, and it goes back up. What will we do then?
That would be more of a conservation of momentum problem, because now you're dealing with collisions. So now you need to, is the collision elastic? Is it inelastic? Because if the collision's perfectly inelastic, then
it'll just not go up.
Yeah, exactly. If the collision's elastic, it'll stick. But if the collision's perfectly inelastic, that means when they collide, they go separate ways. And it's perfectly inelastic, it means it's gonna collide and go back up. Or am I wrong? Wait, I might be wrong.
I'm pretty sure elastic means it's bouncing.
I think you might be wrong. I think you might be right. Yeah, you're right. It's the opposite way. Yeah, if the collision's perfectly elastic, then it's going to bounce and it's going to go right back up to the height that it came from, and then it's just going to keep going. But now if the collision's inelastic, which we know when you collide with the ground, it's going to lose some energy. Then we know that to be true. Okay. Then it's not going to go all the way back up. It's going to go up a certain amount depending on the velocity and all that. But that's more of a conservation of momentum problem, which we'll talk about next unit. Okay?
Yeah.
All right. So non-conservative forces, NCF, non-conservative forces, have no associated potential energy. All right? So they do work on a closed path. What does that mean? Right? Because here we do zero work in a what? What the hell did I write? In a closed path. In a closed path. One that returns to the starting point. That's a closed path. One that returns. Alright, sorry, I forgot to write that part. So non-conservative forces have no associated potential energy. That means they do work on a closed path. Do work on closed path. So here, if we roll a ball, right, from here to here, what does the work do to friction?
work. Work becomes.
What is the
I mean,
work due to
friction. No, friction.
What direction is the
work
force of friction? What direction is the force of friction?
It
Opposing.
counter to movement.
Yes.
So yeah, it's
what-
always negative.
So
right?
the work due to friction is what?
Negative.
Negative. Yes. But now here's the difference. When we roll the ball back, what else? What direction is the force of friction now?
Also counter. It will be
Also
It will
counter
be
to
the
the
opposite
movement.
direction of the movement.
So this
It's-
way. So is the work by friction still does that make the work by friction positive?
Nope, still negative.
Work by friction is still negative. So it doesn't cancel out. We saw that with conservative forces. You go up, the force of gravity takes energy away from the ball, and then when you go back down, it gives it back in perfect conservation of energy. But here, when you roll a ball and you have friction, that's taking away energy, and then when you roll it right back, it's still taking away energy. It doesn't give energy. It only takes it away. It only dissipates energy.
So that's a more accurate term to separate conservative and non-conservative forces, pretty much.
Yes.
They'll always act the exact same, no
Yes.
matter what direction you're going.
Yes. And then they do path dependent work. So wrong color. They do path dependent work. Do path dependent work. Because in this example, our ball goes up and then down, but we only really care about the difference between the starting position and the ending position. But here, if we have a ball that's rolled this way and then rolled back a little bit this way, that path matters, because then we're going to have all of this negative work and this little bit of negative work. Make sense?
Yeah.
This is extra negative
friction
work.
force.
Exactly,
Yeah.
extra negative work, and there's no counter to it. So the path does matter. It does matter if it goes forward and back. You're not just looking at final and starting positions anymore. You're looking at every single position. It's every time it's switched directions, because now you have negative energy. All right, got it. Those are non-conservative forces. Any questions?
No, but let me just. Can you just stay here for a minute? So I could probably.
Yeah, I got you.
I got it, but just.
All right. We're gonna go on a quick intermission, y'all, on the stream. So Jacob can copy this down, and then when we're back, we'll go ahead and go with the amazing, wonderful derivation of work and force. It'll be very fun. So stay tuned for that, and we'll be back soon.
Under the oak tree, the swing creaks slow, bare feet brushing the grass below. Moonlight spilling on your golden hair. Under the oak tree, the swing creaks slow, bare feet brushing the grass below. Under the oak tree, the swing creaks slow, bare feet brushing the grass below. Moonlight spilling on your golden hair. I take a deep breath, you're unaware. My hands are nervous, I grip the chain. Words in my chest like falling rain. I steal a glance, your cowboy grin, wondering if I should let you in. Swinging hearts beneath the stars, I confess I've loved you from afar. I walked into the kitchen late last night, saw the jar glowing in the fridge light. The craving hit like a thunderclap. Tonight I need more than a midnight snack. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four, just for you. Sweet delights and love, it's a bite overdue. Chocolate chips like his dreamy eyes, sugar's melting under moonlit skies. He's got the crunch, he's got the charm, wrapped in love that could keep me warm. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four, just for you. Sweet delights and love, it's a bite overdue. Mix the dough with a pinch of fate. Careful now, don't overbake. Heart-shaped sweetness soft inside. A spoonful of love to keep the vibe alive. No calories can measure this sweet deal. He's got the flavor, he's almost unreal. Milk and cookies under the neon signs. A recipe for love you can't redefine. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four, just for you. Sweet delights and love, it's a bite overdue. Chocolate chips like his dreamy eyes, sugar's melting under moonlit skies. He's got the crunch and love, he's got the crunch and love, it's a bite overdue. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four, just for you. Sweet delights and love, it's a bite overdue. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one.
Y'all, we are back. Oh, you can hear the stream reverb in the background. Oops. Alright guys, we're back now. So we're gonna go ahead and get started. Ignore the picture of my grandma. So let's go ahead and continue. Got the notes. Alrighty. So we left off. Alright, so now we're gonna derive a relationship between work and force. Alright. So this is the work-force derivation in the simplest of cases. Simple case. All right. So a hockey puck. So in this case, we're gonna look at it like this. All right. Oops. Or whatever. All right. A hockey puck. Hockey puck rests on ice, so it's frictionless. All right. The stick pushes with a constant force. Stick pushes with constant force. Oops. With constant force of 50 newtons. All right, over 30 centimeters. So we know that when you push something with a force, when you apply a force, what happens?
The force moves in the direction.
The force moves. The force does not move.
The object moves in the
the
direction of the force.
What else?
And you gain resistance from friction.
It's frictionless track. What else?
Oh, sorry. What else?
What else? What else happens when I apply a force to something? Let's say I'm standing still, and I apply a force. What happens to the object?
The object, of course, like I already previously said, moves in the direction.
It starts moving, right? But what does the
Yeah.
force exactly do? What kind of movement does the force create? It blank the object. It accelerates the object. I'm just gonna say, the force accelerates the object, right?
Yeah.
What does that mean in terms of energy?
In terms of
What is the
energy,
force doing in terms of energy?
it's using more energy.
No, the force. What? No. What is it doing in terms of energy? If I'm accelerating an object, what am I doing? Let's break it down. When I accelerate an object, what changes?
The
more
position.
Kinetic energy.
Uh, what? What'd you say, Jacob?
More kinetic energy.
More kinetic energy. Perfect. You skipped straight to the point I was trying to make. When I apply a force, I gain kinetic energy. What does that mean when I gain kinetic energy? The force is doing
Work.
work. All right. So how can we relate force to work? So how much work does the stick do is the question we're posing, right? How much numerically, we're trying to make a numerical relationship between force and work. Because what happens when we have a numerical relationship between force and work, we have a numerical relationship between force and the change in kinetic energy. We have a numerical relationship between force and mechanical energy. And we have a numerical relationship between force and kinetic energies and positive and potential energy. So how much work is done by force? Work is done by that force. So force gives rise, so a force gives rise to work and kinetic energy, because a object, work and kinetic energy. A object needs a force to move, to accelerate, to change its kinetic energy, to do work. All right. Without a force, it would not be possible. The object would just stay at rest with zero energy. It needs to gain its energy from something, from a force. Right. You can't gain energy from something without a force. Like, if you can name right now a situation in which you gain energy from something that does not involve using a force, I'll give you $100.
Okay.
All right. So let's continue. So let's use this kinematic relationship. Let's use that. The V2 squared is equal to V1 squared. V1 being initial, V2 being final.
So what happened?
Hold on. Sorry. I was figuring something out. Alright. So plus 2a delta x. Alright. So v squared is v2 squared plus v1 squared, or is equal to v1 squared plus 2. We know that a is equal to A is equal
Acceleration.
to
Force times mass.
force times mass.
What?
Are you sure about that?
No, I'm not sure.
Force divided by.
Force divided by mass.
Yeah,
Correct.
force
Jacob.
divided.
Delta x. We solve, we get 1/2 mv squared squared minus 1/2 mv1 squared is equal to f delta x, correct?
Yes, it is.
So the change in kinetic energy is equal to F delta X. So work is equal to F delta X. And this is a constant force in the same direction. In the same direction as displacement. All right? So in this example, we have 50 newtons across 30 centimeters, so 0.3 meters, is equal to 15 joules. All right? And we know that a joule is 1 Newton meter is equal to 1 kilogram meter per second squared
Brother.
times meter, and that's 1 joule. All right? So let's go ahead and sketch. So we're going to go ahead now.
Slow down. Teeny tiny bit.
Okay. So now we're going to go ahead and sketch. I'll move up a little bit so you can copy. So now we're going to go
Scroll.
ahead. Huh?
You got it. Alright, I was gonna say scroll slightly up, but you're good. You're good.
Alright. So now we're going to go ahead and sketch f of x for the previous problem. So we're going to sketch the graph of f of x for the previous problem. So f of x, so on our, what's going to be on our y-axis, guys?
Or y-axis. Our position.
Our y-axis will not be our position. This is f of x. If we had y of x, what would be our y-axis?
Oh no, sorry. The x-axis will be x and the y-axis will be f of x.
Yes, so this is our force, and then
Force.
this is our displacement, or x, our position, should I say.
Yeah.
So, our f of x here is just a straight line. It's a constant force at 50 newtons, right?
Yeah.
Yeah.
So, our displacement, which is from here to here, right, creates kind of a little rectangle, right? And the
Yeah,
what's the area of this rectangle?
Base times height, which will be 50 times whatever length x is.
Yeah, but in terms of calculus, what would be the area of this in terms of calculus?
The area will be 50n times x.
No. In terms of calculus, what is the area here?
In terms of calculus, the integral.
The integral. Yes, correct. Good job, Jacob. This is the integral
Area, yeah.
of f of x, which is equal to the work. All right, that's another way to represent it. And again, work is equal to F delta X. All right. So what if the hockey stick is applied a varying force? Now it's no longer a constant force. The force varies from position to position. All right. Initially we're applying 10. Then 1 meter later we're applying more. Like, we're speeding up. You're kind of like, you're the hockey player and you're speeding up as you're pushing the stick. So as you move, you speed up, right? And as you speed up, you're applying more force relative to your position, right? Because the faster, if you're running, you're speeding up. And you're speeding up relative to the distance you run, correct?
Yes.
All right. So how would that look like? Let's do it on a different page. Are we good here?
Yeah.
All right. So now, let's say the hockey stick applies a varying force. Hockey stick. Let me check something. Hockey stick applies varying force. So let's say the hockey stick applies a varying force. What's that going to look like? What's the work going to look like? If both of you can guess right now, we'll stop tutoring for today.
What?
If both of you can guess how to calculate the work done by a varying force, we're done with tutoring for today.
How to calculate the work done by a varying force.
Yes. I slightly mentioned it in the previous page. That's why I want to do this on a different page. And I give it away.
Is it work is equal to the force AV delta x?
You Googled that.
No,
You Googled that. Yes, you did.
I didn't Google that.
Yes, you did, because there's no way. That's the end of the problem. That's not the beginning of it. No. And you use such specific denotation that I know you Googled it.
Dude, you know you're streaming your screen, right? On your computer.
Oh, I am?
Yeah.
Oh! Bruh! I did not know that! Well, you're wrong anyways. Yeah, of all the things... Robin, the answer was on the screen and you still got it wrong. Well, in that case, since the notes are compromised, then you lose that opportunity. You should have said anything, Robin. See, I would have believed if you said the correct answer. I would have believed you. All right, but let's just go ahead and do it.
Oh, come on, dude. Give it a try. I didn't even look at. I just looked at the end. I didn't even look at the actual answer.
All right, F. All right, we got the F and X, right? And this is what a varying force looks like, right? right?
Yeah.
All right, good. I'm glad I'm on the same page. So, remember, what is the workforce theorem say? What does it say?
Workforce.
What does it say? It says that
the
F
net
delta
work.
x, right? So it's the area under the curve of F delta x from here, let's just say from here to here, for example.
And that's work.
What is this? This is going to be a bunch of teeny tiny rectangles with teeny tiny areas. All right, teeny tiny rectangles with teeny tiny areas. All right, and each of these teeny tiny rectangles has a very small, let me do this on a smaller pen, has a very small dx, and this is what? What is that? What is the length of this?
The length.
What is the length of that? It's f of x.
Right.
Because it's dependent on the position. Here, let's say that this is x is 0.2. That's going to be f of 0.2, which is going to be this. But here, let's say that this is 1. F of 1 is going to be this, correct?
Yeah.
Right? Which is the length, because from 0 to 1 is 1, correct?
Yeah. From 0 to 1 is 1.
Make sense?
It makes sense.
So if we sum up all of these teeny tiny areas, sum of all the small areas, we should get our work
Work.
by f of x, right?
Which is it? Delta K.
Delta.
K E.
Where did you get ke from? Where did you get k from?
Kinetic energy.
Oh, no. That's not what I'm talking about. No.
Okay.
So if we sum all the small areas of dx times f of x, we should get our total work, right? So what would that be? The sum of all of our teeny tiny areas. What would that be? Huh?
It's just
So, okay, wait. Here's a better way to put it. These small areas do small work, right? Each force over tiny displacement does a tiny bit of work, right? Oh, hold on, guys. We're
Jacob, what's your deepest, darkest secret?
all right, Robin, focus. So,
Okay.
so we have a teeny tiny area that does a teeny tiny amount of work, right? So what would that look like? That would be dW is equal to f dx, right? This teeny tiny area right here does a teeny tiny amount of work, right?
Yeah.
Correct? We understand how that teeny tiny area is equivalent to a teeny tiny amount of work, correct?
Yeah. It's one part of the overall work. Which
So
is
if
the
we
entire-
sum up all of the teeny tiny areas, we'll get our total work, right?
Yeah.
So what we do is we integrate. So our total work is equal to the integration of f of x dx from x1 to x2.
Okay.
Got it?
Yeah.
yeah.
So this is a tiny amount of displacement. Tiny amount of displacement for a tiny amount of work. All right. This is better put here. And this would be the sum of all the infinitesimally small, rectangles whose area is work. So let's take a step back for a second. we were able to determine here that a force over a displacement is our work, right?
Yeah.
Correct? And here we were able to when we graphed it, we were able to see that the area under the curve
Is work.
is work. In this case, it was a rectangle, so it's f of x times dx. This is dx right here. This is, or delta x. This is delta x, right? And then this is f of x. So f of x times delta x, which is the area under the rectangle, is equal to our work, right?
Yes, sir.
Yes. Now, when we have a curve, when it's not constant, when we have a curve, we still have those tiny those rectangles of work. They're just infinitesimally small. And if we sum those infinitesimally small rectangles whose area equals work, then we get the total work done by the force, right?
Yeah.
And the smaller it gets, the more accurate it is. That's why we integrate. Because when we integrate, they're infinitesimally small points. All right? Any questions?
No, that makes sense.
Yeah, it's straightforward.
Yeah, and then
It's just
if
the
for whatever,
integration
and
from
then
X to
and then if we
V.
have this area right here, we have this curve. Let me just copy and paste this to simplify my life. Then here, this is our work. Oops. This is our work. And if we wanted to find our average force, we would have all of this, and then this be our average force. All right. What that indicates is that work is equal to F average delta X. All right. So if we know, okay. So if our work is if our work is the integration from x1 to x2 of f of x dx, if we know how much work that is, then we can find our average force simply by dividing by that displacement. Okay.
Yeah.
Which takes us back to the calculus equation. I don't know if you guys remember 1 over b minus a integration of a of b of f of x dx. That's what that is. What is b minus a? That's our delta x. So 1 over delta x integration of x1 to x2 of f of x dx, and that's our average force. All right?
Yeah.
Got it?
Yes, sir.
All right, let's do an example. If you guys got it, then we can do an example by all means. So let's go ahead and do an example. All right, so. Hmm? No. All right, so let's do an example. This is gonna be example 18, and I'm gonna put up the example, and we're gonna take a quick intermission. And they're gonna do the example. When I come back, we'll check the example together. So this is example 18 or 19? Example 18. All right. So we have a puck that is pushed with varying force F. A puck with varying force F. The varying force looks a little something like this. I'm gonna have a box here that goes down like this, and then kind of becomes a proportional relationship here. This is 0.1, this is 0.2, this is 50, and this is 100. All right, this is X, this is F. What is the mass of the object? Mass is equal to 0.105 kilos. What is V final? All right.
Okay.
So go ahead. We're gonna take a quick intermission for the beautiful people on the stream. When I'm back, we're gonna go ahead and continue this. All right?
Yeah.
Okie dokie.
All right. Peace out. Talk soon. Going on intermission.
I walked into the kitchen late last night. Saw the jar glowing in the fridge light. The craving hit like a thunderclap. Tonight I need more than a midnight snack. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four just for you. Sweet delights and love, it's a bite overdue. Chocolate chips like his dreamy eyes. Sugar's melting under moonlit skies. He's got the crunch, he's got the charm. Wrapped in love that could keep me warm. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four just for you. Sweet delights and love, it's a bite overdue. Mix the dough with a pinch of fate. Careful now, don't overbake. Heart-shaped sweetness soft inside. A spoonful of love to keep the vibe alive. No calories can measure this sweet deal. He's got the flavor, he's almost unreal. Milk and cookies under the neon signs. A recipe for love you can't redefine. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four just for you. Sweet delights and love, it's a bite overdue. Chocolate chips like his dreamy eyes. Sugar's melting under moonlit skies. He's got the crunch and love. He's got the crunch and love. It's a bite overdue. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four just for you. Sweet delights and love, it's a bite overdue. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four just for you. Sweet delights and love, it's a bite overdue. Mix the dough with a pinch of fade. Careful now, don't overbake. Heart-shaped sweetness soft inside. A spoonful of love to keep the vibe alive. No calories can measure this sweet deal. He's got the flavor, he's almost unreal. Milk and cookies under the neon signs. A spoonful of love to keep the vibe alive. I walked into the kitchen late last night. Saw the jar glowing in the fridge light. The craving hit like a thunderclap. Tonight I need more than a midnight snack. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four just for you. Sweet delights and love, it's a bite overdue. Chocolate chips like his dreamy eyes. Sugar's melting under moonlit skies. He's got the crunch, he's got the charm. Wrapped in love that could keep me warm. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four just for you. Sweet delights and love, it's a bite overdue. Mix the dough with a pinch of fade. Careful now, don't overbake. Heart-shaped sweetness soft inside. A spoonful of love to keep the vibe alive. No calories can measure this sweet deal. He's got the flavor, he's almost unreal. Milk and cookies under the neon signs. A recipe for love you can't redefine. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four just for you. Sweet delights and love, it's a bite overdue. Chocolate chips like his dreamy eyes. He's got the crunch in love. It's a bite overdue. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four, just for you. Sweet delights in love, it's a bite overdue. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four, just for you. Sweet delights in love, it's a bite overdue. Mix the dough with a pinch of fade. Careful now, don't overbake. Heart-shaped sweetness soft inside. A spoonful of love to keep the vibe alive. No calories can measure this sweet deal. He's got the flavor, he's almost unreal. Milk and cookies under the neon signs. A spoonful of love to keep the vibe alive. I walked into the kitchen late last night. Saw the jar glowing in the fridge light. The craving hit like a thunderclap. Tonight I need more than a midnight snack. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four, just for you. Sweet delights in love, it's a bite overdue. Chocolate chips like his dreamy eyes. Sugar's melting under moonlit skies. He's got the crunch, he's got the charm. Wrapped in love that could keep me warm. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four, just for you. Sweet delights in love, it's a bite overdue. Mix the dough with a pinch of fade. Careful now, don't overbake. Heart-shaped sweetness soft inside. A spoonful of love to keep the vibe alive. No calories can measure this sweet deal. He's got the flavor, he's almost unreal. Milk and cookies under the neon signs. A recipe for love you can't redefine. Give me a cookie, give me a man. Give me a cookie that's built like a man. Give me one, give me two, give me four, just for you. Sweet delights in love, it's a bite overdue. Chocolate chips like his dreamy eyes. Sugar's melting under moonlit skies. He's got the crunch and love. He's got the crunch and love. It's a bite overdue. Give me a cookie, give me.
Alright, and we are back. So, let's go ahead and look at the problem. So, what'd you get, Robin?
I got the final force is VF is equal to 17.32.
That is incorrect.
Okay.
Alright, so let's take a look. See. So we know that the work is the mechanical energy transferred to the puck which is equal to K2 because K1 is 0, okay? K2 minus K1, K1 is 0, K2, alright?
Yeah.
So our work is equal to 1/2 mv squared, mv final squared, right? So what is our work? Hello?
Work,
what does work equal?
1/2 mat, that's...
Hello? What does work equal?
Work is equal to
1/2...
the integration of the integration of FFCS.
Yes, correct. What's our integration here? Well, our area. So for our area, you can divide this thing into 3 easy shapes. Or honestly, not even 3 shapes. You could probably divide it
Just
into
2
one.
shapes: the triangle and the square. And the
Alright,
square
this right here,
is base times height.
and then this right here. That's 0.1 times 100.
10.
My mom's calling me. Hold on. Dime. Boy. Alright, once I answer this question, I'll be right back. We're on another intermission. So this is 100 It's 100
Times
0.1,
0.1.
which you said is 10, plus 2.5. I'm just gonna tell you that already. It's 2.5, which is 12.5 joules. All right, this is 12.5 joules, and 12.5 joules is equal to 1/2 0.165 times V final squared. V final, I'm just going to skip some steps here, is equal to 12.3 meters per second. Where'd you go wrong, Robin? Oh, I gave you the wrong mass. That's why. I'm sorry. That's my fault. Yeah, then you'd be right with this mass. 0.16.
Okay.
All right. So we're going to take a quick intermission. When I come back, we're going to talk about a force through no displacement and a constant force
I have to go eat now.
at an angle. Okay, so are we ending the stream then?
I guess we are.
Alrighty. Thank you guys for
Okay.
coming. We're ending the stream. Hopefully we can start up another one tonight to keep going because, like I said, we are on page 8. So, bye guys.
We're missing. Yeah. See you guys.